Hello everyone. Today we are going to discuss about the common collector configurations. As we know already, in the transistors, there are three configurations: common emitter configurations, common base configuration, and a common collector configuration. Based on the terminal is connected to ground, there are three configurations. Today we are going to discuss about the common collector configurations. Now let's discuss about let's see the circuit diagram of the common collector configuration. This is the circuit diagram of the common collector configuration. In this, collector is connected to ground. In the transistor, there are three terminals: emitter, base, and the collector. In this transistor, the collector is connected to ground. That's why it is called as a common collector configuration. In this collector is common to base and the emitter terminal. Here we are using NPN transistor. In the NPN transistor, emitter current direction is outside. Here, see here, emitter current direction is outside, and the base and the collector currents are the inside. Okay, based on the emitter current direction only, we can say whether it is NPN or PNP transistor. Here, emitter current direction is outside, and the base and the collector currents are inside. Okay, in the circuit diagram, if you see the parameters in the circuit, okay, this is called as VBC. And next one, it is the VEC. Okay, let's discuss what is this all the parameters here. The parameters in the circuit, VBC is called as a base to collector voltage. It is a base to collector voltage. The voltage between base and collector it is. Next, VEC. VEC is the voltage between the emitter as well as the collector. Next, this VEE is called as the emitter biasing voltage. This VEE is called as a emitter biasing voltage, and the VBB is the base biasing voltage. This is the VBB, base biasing voltage. We are giving the supply to the base. That's why it is called as a base biasing voltage. Here we are giving the supply to the emitter. It is an emitter biasing voltage. Next, IE. IE is the current passing through the emitter terminal. Okay, now IB. IB is the current passing through the base terminal. That is called as a base current. Next, RE. RE is called as the emitter resistance. The resistor is connected to the emitter terminal. That is emitter resistance RE. Next, the base resistance. Okay, the resistance is connected to the base terminal. That is the base resistance. These are the parameters of the common collector configuration. Now, let's see what are the input parameters. This is VBC and it is VEC. Okay. If you see the input parameters here, if you see that this is a transistor, for this transistor, this left side of the parameters are called as the input parameters and this right side is called as the output parameters here. If you see the input parameter, this is the base current. This is called as the input current. Okay, IB is equal to base current, that is the input current. Next, VBC. VBC is called as a base to collector voltage and it is the input voltage. This is the input voltage and it is the input current. But this is not the input voltage. This is called as a biasing voltage, base biasing voltage. Giving the external supply to the any electronic device is called as a biasing. This is the biasing voltage. There are two biasing voltages here, VBB and VEE. IB and VBC are the input current and the input voltages. Next, if you see the output parameters here, in the output parameter, this is the IE. IE is called as the emitter current, that is the output current. And next, VEC is called as the voltage between the collector and the emitter and it is the output voltage. This is the input and output parameters, IB, VBC, IE, VCE. Okay, now let's see the input current and the output current and the output voltage and the input voltage equations. This is VBC and it is a VEC. Okay, now let's apply KVL at the input side. If we apply the KVL at the input side, we will get the input current equation and the input voltage equation. Now let's apply the KVL at the input side. See here in this loop, IB current is flowing. Okay, this IB current flowing in the clockwise direction. this is a plus terminal and it is a minus terminal, and it is a plus and it is a minus. This IB current flowing in the clockwise direction. Now the current is flowing from minus to plus, plus VBB, plus VBB, and plus 2 minus minus VBC is equal to, and the voltage drop is IB into RB is equal to IB into RB. This is equation number 1. Okay, from this equation number 1, from equation number 1, now we will separate the input current. From equation number 1, input current is indicated by IB. In the, if you see, input current is IB. If you separate IB from the equation number 1, we will get VBB minus VBC divided by RB. This is the input current equation. From the equation number 1 only, if we separate the input voltage, separate input voltage. Here, input voltage is what? VBC. Separate the VBC from the equation number 1. VBC is equal to VBB minus IB into RB. Okay, this is about the input current and the input voltage equations of the common collector configuration. Okay, now let's apply the KVL at the output side. If we apply the KVL at the output side, we will get the output current and the output voltage equation. Now let's apply. In this, the emitter current direction is flowing in the clockwise direction. Okay, now let's apply the KVL here. Here it is a plus terminal, it is a minus terminal, and it is a plus terminal, and it is a minus terminal. So as the current is flowing in the clockwise direction, plus 2 minus minus VEE and minus 2 plus plus VEC is equal to, and the voltage drop is IE into RE. Voltage drop is IE into RE. Okay, assume that it is equation number 2. From equation 2, output current, from equation 2, output current is equal to, from equation 2, output current is given by, so output current is indicated by IE. Separate IE here. If we separate IE is equal to, we will get minus VEE plus VEC divided by RE. This is the output current equation. Now, if we take the output voltage equation, from the equation number 2 only, separate output current, output voltage. Output voltage is indicated by VEC. VEC is equal to, what we will get? We take the VEC, we will get IE RE plus VEE. IE RE plus something is wrong here. Plus 2 minus minus. Okay, nothing issue here. IE RE plus VEE. Okay, this is the output voltage equation. It is the output current equation. IE is equal to minus VE plus VEC divided by RE, and the output voltage is indicated by VEC. VEC is equal to IERE plus VE. This is the output voltage equation. This is about the input voltage, input current, and the output voltage equations of common collector configuration. Okay, now let's see the output current equation in terms of gain, input current, and the IC naught. Okay, now let's see what is the equation we will get. So output current equation formula is equal to output current is equal to gain into input current plus 1 plus gain into IC naught. Here IC naught is equal to reverse saturation current. Now if you see the gain of, since gain of common base configuration is indicated by alpha, and the common emitter configuration is indicated by beta, and the common collector is indicated by gamma. Alpha, beta, gamma are the gains of the common base, common emitter, and common collector. Now let's apply these gains and the output current and input current equation in the formula. The output current of the common collector configuration is indicated by IE. IE is output current is equal to, okay, gain of the common collector configuration is gamma into the input current is indicated by IB. Input current is indicated by IB. Input current is indicated by IB plus 1 plus gain. Gain is indicated by gamma and IC naught. This is the output current equation of the common collector configuration. If you observe the equation, this is the output current and it is the input current. There is no voltage term in this equation. From this we can say that this output current is depends on the input current. That's why this BJT is a current control device. So there is no voltage term here. That's why it is a current control device. The output current IE is depends on the input current IB. Hence, BJT is a current control device. So BJT is a current control device as there is no voltage term in the equation. Okay. Now, if you see the input characteristics and the output characteristics of the common collector configuration, this is the input characteristics. These input characteristics are drawn between the input current and the input voltage at constant output voltage. Input current and the input voltage are variables, and the constant output voltage VC is a constant. So now, if you see the characteristics here, this is the input current and it is the input voltage. Initially, if you increase the input voltage VBC, there is no change in the IB. IB is equal to 0. Up to here, there is no change in the IB. But after reaching to this point, the IB is increases. Okay. Now, if you increase the output voltage, initially the output voltage is VC1. Now, if you increase the output voltage and keeping the constant, and if you increase the VBC, that is the input voltage continuously, so up to this point, there is no change in the current here. After reaching to this point, okay, if up to this point, we have to increase the input voltage. After increasing the input voltage, the input current increases slowly. Okay, so at VCE2, okay, at VCE1, the current starts conduct from this point. At VCE2, the current starts conducting from this point. This input is variable and the IB is variable, but VCE1 and VCE2 are the constants. Okay, if you summarize the characteristics, from the characteristics, it is observed that when the input voltage VBC is increased, initially there is no current produced. See here, initially up to this point, there is no current. Further, when it is increased, the current IB increases steeply. If you increase VBC continuously and after reaching to this point, it increases at VC1. At VC2, Up to this point, there is no conduction. After reaching to this point, it starts increasing. And it is observed that if you increase the further VCE, okay, it is increased, the curve shift towards the right side. Okay, if you increase the VBC further, okay, and that VC1 increased from VC2, the curve shift towards the right side. So this is about the input characteristics of the common collector configuration. Now, if you see the output characteristics, these output characteristics are drawn between output current and the output voltage at constant input current. Output current and the output voltage are variable and the input current is constant. Output current is IE, output voltage is VCE, input current is IB. If you see the characteristics here, so these are the output characteristics of common collector configuration. Output characteristics are drawn between output current and the output voltage at constant input current. Okay, if you increase the VCE up to reaching to this point, okay, IB increases slightly. IE increases slightly. After that, IE is constant. At IB is equal to 0, constant current. If you take the IB is equal to 10 microamps of the constant current, if you increase the VCE, the IE increases up to this point. After that, IE is constant. Similarly, if you take the IB is equal to 20 microamps, and if you increase the VCE, the IE increases up to this point. After reaching to this point, IE is constant. Again, if you increase the IB to the 30 microamps, okay, if you increase the VCE, IE increases up to this point. After reaching to this point, the IE is constant. Similarly, at IB is equal to 5 to 40, IB is equal to 50, and IB is equal to 40 microamps. So like that, up to reaching to this point, the current is increases linearly. After that, the current is constant here. Okay, now let's discuss about the regions here. Okay, output characteristics of the three operating regions. In that, first one is a saturation region, and the second one is a cutoff region, and the third one is an active region. Now let's discuss what is saturation region. Okay, in the saturation region, if you observe, this is the NPN transistor. In this, there are three terminals: emitter terminal, and it is a base terminal, and it is a collector terminal. It is having the two junctions. The first one is emitter junction. Okay, and the second one is the collector junction. Okay, emitter junction and the collector junction. In this emitter junction, it is forward bias. The collector junction is also forward bias. As both the junctions are forward bias, emitter junction and emitter junction as well as the collector junction both are in the forward bias condition in saturation region. Due to the forward bias of the both the junctions, more amount of forward current flowing in the transistor. Okay, as the more current flowing in the transistor, the region in this region, the resistance is very low, and the transistor acts as on switch in the saturation region. If we take the cutoff region, in cutoff region also, it is a emitter terminal, and it is the base terminal, and it is a collector terminal. It is a emitter junction. It is a collector junction. In this emitter junction, it is reverse bias. In this, the collector junction is also reverse bias. Okay, both the junctions are in the reverse bias in cutoff region. Due to the reverse bias of the both the junctions, the current flowing is very low, and the resistance offered in this region is very high. Okay, that's why in cutoff region, transistor acts as off switch. Okay, now let's see about the active region. In active region also, it is a emitter terminal, it is a base terminal, and it is a collector terminal. Okay, it is a emitter junction, and it is a collector junction. In the active region, emitter junction is forward bias, and the collector junction is reverse bias. Okay, Due to the forward bias of the emitter junction, the current flows in the emitter junction is very high, as it is forward bias. Due to the reverse bias of the collector junction, the current flows in the collector junction is very low, as it is reverse bias. So from this we can say that in active region, transistor acts as amplifier. What is amplifier? It increases the signal strength of the input signal. Okay, increasing the signal strength is called as an amplifier. So from this we can say that transistor acts as an amplifier in the active region. Okay, the transistor is having the three regions. Okay, active region, cutoff region, and the saturation region. In the active region, the transistor acts as an amplifier. Okay, this is about the input and output characteristics of the common collector configuration. In the next class, we will discuss about the common base configuration.